So now we'll talk about section 2.2, covalent compounds, as opposed to ionic compounds. Now, as opposed to trading electrons between cations and anions, covalent bonds between atoms consist of shared valence electrons. So a set of atoms joined by covalent bonds is called a molecule, and most of the substances around us are covalent compounds, like water, CO2 or carbon dioxide, gasoline, paper, cotton, plastic, sugar, plant life, cosmetics, tires. This is certainly not an exhaustive list. So this is just a few examples of covalent compounds. Most substances are covalent compounds. And the properties of these covalent compounds certainly differ from ionic compounds due to the different nature of their bonds. So ionic compounds have a high boiling point. Covalent compounds have relatively low boiling point. Ionic compounds have a high melting point. Covalent compounds have a low melting point. Ionic compounds have solutions that conduct electricity. Remember our discussion of electrolytes. Covalent compounds have solutions that do not conduct electricity. Ionic compounds are usually solids. Covalent compounds can be solids, liquids, or gases. They can come in all three phases. So instead of the formula unit, it's the molecular formula that lists the number and type of each atom per molecule. So example, water, H2O. There are 2 hydrogens, 1 oxygen for each water molecule. And different formulas now will represent different compounds. H2O is water, but H2O2 is completely different. It's called hydrogen peroxide, and it has different reactivity and different properties than water does. So each covalent bond consists of a pair of shared electrons, and we indicate that covalent bond either by a line between atoms or 2 dots. I prefer the line. I think the book uses the line more often, but you could think of it as 2 dots make up this line, meaning the line represents 2 shared electrons. So we think of it as the hydrogen atom has 1 proton and 1 electron. It combines with another hydrogen atom, and both hydrogen atoms will share those 2 electrons, so that each can think of it as having 2 electrons in the valence shell, so having a full octet. So diatomic molecules contain 2 atoms. Some common examples: hydrogen, oxygen, nitrogen, fluorine, chlorine, iodine, all have just 2 atoms in their molecular formula. And so, for instance, chlorine has a total of 7 valence electrons. And if each chlorine contributes 1 electron to a shared pair of electrons, you'll see that each of these circles then, if we count these 2 twice, has 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So by sharing 1 electron of each chlorine can then have a full octet. Shared electrons are part of the valence shell, and as we said, sharing seeks to achieve a filled octet. So here's another example with methane, CH4. Carbon has 4 valence electrons. Remember that carbon is right here. It has a total of 6 electrons. 2 of them go in the n equals 1 shell, and that leaves 4 to go in the higher energy n equals 2 shell. Those 4 electrons are the valence electrons for carbon. Hydrogen has 1 valence electron, only 1 electron total, so it has to be the valence electron. And if we arrange the hydrogens around the carbon properly, both carbon and hydrogen will have a full octet. So we see that the carbon brings 4 electrons to the table. Each hydrogen brings 1 electron for a total of 8. 4 plus 4 times 1 is 8. So the carbon is surrounded by 8 electrons. Each hydrogen shares a bond with the carbon where it possesses, or it shares, those 2 electrons, and so each hydrogen has a filled octet as well. Octet meaning 2 valence electrons for a hydrogen. As we said before, chlorine looks like this, where we have 1 shared pair. Each chlorine donates 1 electron to the shared pair, so that each chlorine can have a full octet, even though they are sharing 2 of the electrons. Can we share more than 1 pair? Yes, we can. So 1 pair of shared electrons is called a single bond. 2 pairs is called a double covalent bond, and 3 pairs is called a triple covalent bond. And the single bond is longest, the triple bond is the shortest in terms of the bond length. So here's an example of 2 shared pairs of electrons. Ethylene looks like this. Each carbon shares 2 pairs with the other carbon. They still have 8 electrons surrounding them, except that 4 of them are shared with the other carbon, and 4 of them come from the 2 hydrogens, or are shared with the 2 hydrogens. And this is the only way these 2 carbons could achieve the noble gas configuration. They have to share a total of 4 electrons. Here's an example of 3 shared bonds, or a total of 6 shared electrons in acetylene, C2H2. Each carbon shares 3 pairs of electrons with the other carbon, and 1 pair with a hydrogen on the other side, again achieving a full octet for each carbon. So Lab 3 is going to deal with Lewis structures. We'll briefly discuss them here. I encourage you to read the section in the book. There's a little bit of Lewis structures on the WebAssign homework and in certainly the lab. So we'll discuss them here, and then the lab can bring you up to speed more on Lewis structures. There'll be a video for that lab as well. So a Lewis structure shows the bonding electrons in a molecule. We can show them either as dots or as lines. And they also will show non-bonding electrons, and Lewis structures are essentially a way for us to keep track of electrons. So here we'll show the Lewis structure of water, and we want to show that right here we observe that not all the valence electrons are shared. Shared electrons are the bonding electrons, and they appear as these blue lines between the O and the H and the O and the leftmost H. Electrons that are not shared are called non-bonding electrons, and they are shown here as the red dots. So there's 2 non-bonding lone pairs of electrons on the oxygen. And so we have a total of 8 electrons here, 2 from this bond, 2 from this bond, 2 from the lone pair, 2 from the other lone pair. 4 times 2 is 8. And so the oxygen shares or possesses all 8 of these, and each hydrogen shares those electrons in the bond it has with oxygen. So the hydrogens have their full octet at 2, and the oxygen has its full octet at 8. If we look at the Lewis structure of N2, each nitrogen atom starts with 5 valence electrons based on its location on the periodic table. Right here, group number 5A, it has 5 valence electrons. So they start with 5 valence electrons. We need 3 more to have a full octet on each nitrogen. So if each nitrogen shares 3 of its electrons with the other nitrogen, we can provide full octets for both nitrogens. That results in a triple bond. So 3 shared pairs of electrons and 2 non-bonding pairs, 1 on each nitrogen. We draw that more properly. The Lewis structure looks like this: a lone pair on each N, 3 lines between the ends indicating 3 bonds are shared. So the position in the periodic table tells us how many bonding and non-bonding electrons are typically present in compounds containing these elements. So we look at carbon. It's located in row 4. It has 4 valence electrons, and so it typically will have 4 bonding pairs, or 4 covalent bonds with 0 non-bonding pairs. Nitrogen and phosphorus will have 3 bonding pairs and 1 non-bonding pair. Oxygen and sulfur, as we saw with H2O, oxygen had 2 bonding pairs, 2 bonds to H's, and it had 2 non-bonding pairs. The halogens, they all reside in group 7. They only need 1 more electron to become a full octet. So they only have to share 1 bond with other elements, and they have 3 non-bonding pairs of electrons. So how do we write a Lewis structure? The first thing is to identify the central atoms and the surrounding atoms. And initially we'll just place single bonds between those pairs of atoms. So if we start with CH4, one of the rules is that hydrogen is never a central atom. So we'll put the carbon in the center here, and then draw bonds between the carbon and all the H's. Then we need to add up all the valence electrons. We have 1 carbon with 4 valence electrons, and we have 4 hydrogens, each with 1 valence electron. So 4 plus 4 times 1 equals 8 total electrons. So we want to make sure that our drawing reflects that there are 8 total valence electrons present. And so in methane, we see that there are 4 bonds, 2 electrons in each bond, 4 bonds, 8 total electrons. There's nothing more to do. This is the proper Lewis structure for methane, because there are already 8 electrons showing. Sometimes we have more electrons than we have showing initially in the bonds, and so then we would go to distribute the remaining electrons as non-bonding pairs. And then the last thing we want to do is to ensure that each atom has an octet. Most atoms want to have 8 electrons. Hydrogens, of course, only want 1 pair. So we want to check that. Does it make sense? So let's practice that by drawing a couple Lewis structures here together to hopefully reinforce these simple rules that we just discussed. So write the Lewis dot structures for the following: ammonia, oxygen, hydrogen sulfide, and chlorine. Okay, so we have N, 5 electrons. Remember, that's in group 5A. 3 H's equals 3 times 1 electron. 8 electrons total in the valence shell. Remember that hydrogen is never a center atom, so we put the nitrogen, H, H, H. So I've distributed the hydrogens around the nitrogen. I have 1, 2, 3 bonds, a total of 6 electrons. I started with 8, so I should still have 8. We need to distribute 2 more electrons. We will never ever draw a lone pair on hydrogen. Hydrogen always has just 1 bond and it's happy, so that lone pair, the last 2 electrons, need to be drawn on the nitrogen. And now we need to check that each atom here has a full octet. Hydrogen should have only 1 bond, 1 and only 1 bond. Nitrogen has 3 bonds and a lone pair. That adds up to 8 total electrons, so we're good here. Oxygen starts with 6 electrons, so 2 oxygen equals 2 times 6 electrons, total of 12 electrons. There's no central atom, we just have 2 atoms here, so we draw oxygens with a single bond. This accounts for 2 electrons, and we have 12 more. So we need to distribute our lone pairs so that each oxygen will have a total of 8 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8, plus 2 in the bond gives us 10. We're still missing 2 electrons. We could put 2 electrons here or 2 electrons here. That makes a somewhat unsymmetrical molecule. Sometimes we will have unsymmetrical Lewis structures, but in this case we want to keep a symmetrical structure, so we might think of putting 1 atom on each oxygen. But I think we'll see that this oxygen has 1, 2, 3, 4, 5, 6, 7 electrons in its valence shell. It shares 2, it has 5 more. Same with this oxygen. So we don't have a full octet. So if we get rid of this and use them to form a second bond between the 2 oxygens, now we share 2 bonds and we have 2 lone pairs. And each oxygen, I think you'll agree, has a full octet. So this one's good. And also we knew that oxygen had 6 electrons. It needs to share 2 from another oxygen or another atom in order to achieve the full octet. And here we see it's sharing 2 bonds, so that gives it 2 more electrons. Hydrogen sulfide. Hydrogen is never the central atom, so we'll draw it like that. We know that there are 2 H's, 2 times 1 electron. Sulfur. Where is sulfur? How many valence electrons does sulfur have? Sulfur is right over here. Group 6A, it has 6 valence electrons. So we add those up, we get 8 electrons. 2 times 1 plus 6. I'm going to redraw my H2S down here because I've taken up too much room. Now with my bonds that are already there, I have 2 plus 2 total electrons, giving me 4 electrons on my drawing. I'm left with 4 remaining out of my 8. I cannot put lone pairs on the hydrogen, so I have to put a lone pair on the sulfur. That accounts for 2 and 2 more. So 1, 2, 3, 4, 5, 6, 7, 8. That is the proper Lewis structure for sulfur. Now the sulfur has 8 electrons surrounding it. Each hydrogen has 2 electrons surrounding it, which is what hydrogen wants. We've already seen the Lewis structure for chlorine several times. These are 2 chlorines equals 2 times 7 electrons, total of 14 electrons. We know that each chlorine has 7 electrons. It wants one more to share, and that means it should have one bond. So we could distribute the rest of our 14 electrons around as lone pairs. So we took out 2 from the 14. We're left with 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've distributed all the electrons. Each chlorine has 8 valence electrons, 6 from the lone pairs and 2 from the shared bond. So this one matches up as well. Second question asks us to look at the Lewis structure for carbon dioxide shown right here. So how many bonding and non-bonding electrons are on each oxygen? So there are 2 lone pairs on each oxygen, so that's 4 non-bonding electrons. And each oxygen shares 2 bonds with a carbon, so that's 4 bonding electrons. How many non-bonding electrons are on the carbon? Well, we see no lone pairs, so there are 0 non-bonding electrons. How many bonding electrons? There are 4 bonds on the carbon, so we have 8 bonding electrons. Does each atom have an octet? Well, the oxygen has 1, 2, 3, 4, 5, 6 in this bond, 7, 8 in the second bond, so that has an octet. Same with the other oxygen. And the carbon shares 4 bonds, 2 electrons per bond, so yes, each atom has an octet. What types of bonds are present? These are double bonds. Right? These are double bonds, 2 bonds between 2 atoms. Okay, so clicker question 2.4, what is the best Lewis structure for CH2Cl2? Here's a little more tricky. You need to decide which is the central atom. We've already seen examples of molecules with all these 3 types of atoms here, so you should be able to choose what the central atom is. And don't forget to distribute all the lone pairs appropriately. Okay, so what is the best Lewis structure for CH2Cl2? Let me just find some paper here where I can write on it. So CH2Cl2. So the carbon is 4 electrons, 2 hydrogens, 2 times 1 electron, 2 chlorines, 2 times 7 electrons. Let's add those up. 4 plus 2 plus is 6. 4 plus 2 is 6. 2 times 7 is 14. 6 plus 14 is 20. So now whenever we see a carbon as one of our atoms, it's best to assume that that is the central atom. It doesn't matter which way we arrange the rest of the atoms, so long as they all have a bond to carbon. And so now I've accounted for 8 electrons in the bonds, right? 4 bonds. So I have 8 electrons in the bonds, 12 remaining. So where do I put those 12? I put them as in terms of probably lone pairs, but first let's see if any of these 5 atoms have an octet. Hydrogen has 1 bond, it's good. This hydrogen has 1 bond, good. We don't want to add any more electrons to a hydrogen with a 1 bond. Carbon has 4 bonds to it. That makes it has 8 electrons, so it's also good. These chlorines, however, only have 2 electrons. They need some more. Let's fill in our 12 remaining electrons. So we can give each chlorine 3 lone pairs, and that accounts for 12 electrons. And now the chlorines with 3 lone pairs in a bond will have a full octet. 3 lone pairs in a bond. And so that leaves us with the carbon in the middle, 2 hydrogens bound to it, and 2 chlorines bound to it. That means B is the best choice. A is pretty close, except we didn't draw lone pairs on the chlorines. C is not good because the chlorines have 2 bonds to them. We never want to have 2 bonds to chlorine. D has chlorine as the central atom. That's also not a good choice. So B is the best choice here.